Have you ever looked at a map of the world and noticed something peculiar about the shapes of the continents? Look closely. South America and Africa seem like they could fit together, don't they? This seemingly simple observation sparked a revolution in our understanding of the Earth. For centuries, mapmakers and explorers had pondered the uncanny resemblance of coastlines across vast oceans. The idea that continents might have once been joined together like pieces of a giant jigsaw puzzle had been around for centuries. As far back as the 16th century, Flemish cartographer Abraham Ortelius noticed the remarkable fit of the coastlines of Africa and South America. It wasn't until the 20th century that a young German meteorologist named Alfred Wegener dared to challenge the prevailing wisdom. He proposed a revolutionary idea that the continents were not fixed in their positions, but were, in fact, drifting across the Earth's surface. Alfred Wegener, a man of boundless curiosity and a thirst for adventure, was captivated by the puzzle of the continents. He meticulously gathered evidence from various fields, piecing together a compelling case for his theory of continental drift. Fossil records revealed identical plant and animal species on continents now separated by vast oceans. These organisms could not have traversed the oceans as we know them today. How could this be possible unless the continents were once connected? Wegener also pointed to geological evidence, like matching rock formations and mountain ranges, that abruptly ended at one coastline and continued on another across the ocean. The evidence was mounting, painting a picture of a dynamic Earth where continents drifted apart over millions of years. Despite the compelling evidence, Wegener's theory was met with skepticism and even ridicule from the scientific community. The idea of continents ploughing through the solid ocean floor seemed preposterous at the time. The prevailing view was that the Earth was a rigid, unchanging sphere. What force could possibly drive such massive movements of continents? Wegener lacked a mechanism, a way to explain how continents could actually drift. However, the seeds of a scientific revolution had been sown. The answer to the mystery of continental drift lay hidden beneath the waves in the deepest recesses of the ocean floor. During World War II, a new era of exploration began, driven by military necessity. Submarines, equipped with sonar technology, were deployed to map the ocean floor, listening for echoes to reveal the underwater landscape. The sonar images revealed a vast underwater mountain range stretching for thousands of miles across the globe. This immense chain of mountains, known as the Mid-Atlantic Ridge, ran right down the center of the Atlantic Ocean, mirroring the coastlines of the continents on either side. This discovery was a revelation. It suggested that new crust was being formed at the Mid-Atlantic Ridge, pushing the older crust away from the ridge like a conveyor belt. The discovery of seafloor spreading provided the crucial mechanism for continental drift, finally elevating Wegener's once radical idea to a cornerstone of modern geology. The Earth, it turned out, was far more dynamic than anyone had imagined. A new theory emerged, one that unified continental drift and seafloor spreading into a single, elegant framework plate, tectonics. The theory of plate tectonics posits that the Earth's outer layer, known as the lithosphere, is divided into a mosaic of giant moving plates. These plates, some as large as continents themselves, float on a hotter, more fluid layer called the asthenosphere. The heat from the Earth's core creates convection currents in the asthenosphere, much like the currents in a boiling pot of water. These convection currents act as a giant engine, driving the movement of the tectonic plates above. Section 5. Convergent boundaries where continents collide. The dance of the tectonic plates is a slow and powerful ballet with dramatic consequences for the Earth's surface. Where plates collide, buckle and grind against one another, we witness the awe-inspiring forces of nature unleashed. These are the convergent plate boundaries, zones of intense geological activity that have shaped some of the most dramatic features on our planet. Imagine two colossal tectonic plates, each carrying a continent on its back, slowly converging over millions of years. The immense pressure generated by this collision is unimaginable. The Earth's crust buckles, folds, and uplifts, creating towering mountain ranges that pierce the sky. The Himalayas, the Alps, the Andes, these majestic peaks stand as testaments to the immense power of convergent plate boundaries. When an oceanic plate collides with a continental plate, the denser oceanic plate is forced beneath the lighter continental plate in a process called subduction. Section 6: Divergent boundaries, birthplaces of new crust. While convergent boundaries are marked by collisions and destruction, divergent boundaries are places of creation and renewal. Here, tectonic plates move apart, pulling the crust thin and allowing molten rock from the Earth's interior to rise and solidify, creating new crust. The Mid-Atlantic Ridge, that underwater mountain range discovered during World War II, is a prime example of a divergent plate boundary. Here, the North American and Eurasian plates are slowly pulling apart, creating new oceanic crust as magma rises from the mantle to fill the gap. Divergent boundaries are not limited to the ocean floor. In some cases, they can occur within continents, creating rift valleys like the East African Rift. Section 7: Transform boundaries, plates grinding past. Not all plate boundaries are marked by dramatic collisions or the birth of new crust. At transform boundaries, tectonic plates slide horizontally past each other, creating a different kind of geological drama. These boundaries are characterized by intense friction as the plates grind against one another, building up stress that is periodically released in the form of powerful earthquakes. The San Andreas Fault in California is perhaps the most famous example of a transform boundary. Here, the Pacific Plate and the North American Plate are locked in a slow-motion dance, sliding past each other at a rate of about 5 centimeters per year. This movement is not smooth, however. Section 8: Shaping our world, the artistry of plate tectonics. The theory of plate tectonics is much more than just a scientific theory. It's a grand unifying concept that helps us understand the Earth as a dynamic and interconnected system. It's the driving force behind the formation of continents, oceans, and mountains, and it plays a crucial role in shaping the climate and influencing the evolution of life on our planet. The Earth's surface is a canvas, and plate tectonics is the artist, constantly reshaping and remolding the landscape over millions of years. The continents, once locked in a giant supercontinent, have drifted apart, collided, and reassembled over eons, creating the world we know today. Plate tectonics is not just a thing of the past, it's an ongoing process that continues to shape our planet today. Section 9: A dynamic future, the ever-changing face of Earth. As we gaze out at the familiar shapes of our continents, it's hard to imagine them arranged any differently, but the Earth is a dynamic and restless planet, and its continents are not destined to remain in their current configuration forever. The same forces that brought the continents together into supercontinents in the distant past will continue to reshape the Earth's surface far into the future. Geologists predict that in about 250 million years, the continents will once again converge to form a new supercontinent, a single landmass that some have dubbed Pangea Ultima. This future supercontinent will be centered around the equator, with the remnants of the Atlantic Ocean forming a small inland sea. The story of plate tectonics is a reminder that our planet is not static, but a dynamic and ever-evolving system.